Okay, I think it's recording now. Okay, can you guys see my you guys can see my screen, right?
Yeah, I'm not sure if it's recording though, because I don't have a pop-up saying that it's recording.
Okay, but here it shows it's recording.
Okay, I
It
guess it's
is.
just my side then. Okay.
Yeah, I think it is. Okay, let's get started. Okay, so first of all, we have three students here. Thank you for coming. I'm traveling tomorrow. So usually when I travel, I just offer classes online like this. Some professors they just cancel the class, but I don't feel that's fair to you guys. So I will just offer this online. I think today we probably will take hopefully less than 2 hours to finish. So I will still have an office hour tomorrow. If I cannot make it, I will keep you guys posted on Slack. I think I can make it, but it will be online. So if you want to talk about homework, then you can still join my Zoom session to talk about your homework. So today we will talk about format string vulnerability, and we are already entering the second half of the semester. So we spend a lot of time talking about buffer overflow at the beginning, because at that time you also need to build the background for reverse engineering, for a lot of system background. And now we are going to move a little bit faster. So every week we will talk about a new topic, and some of the topics are quite more difficult than buffer overflow. But because of that, it's also more fun. So the topic we are going to talk about is called format string vulnerability. So before we talk about that, we will first talk about C functions with variable arguments. So what is a function with variable arguments? It's a function when the developer programs this function, the programmer doesn't really know how many arguments it will take, right? So when you program a function, you expect someone, maybe not yourself, maybe someone else to use that function, to call your function. But you don't really know how many arguments it will be provided, right? So most of you, when you program in C, the functions you develop there, probably you will call them in the future, you will use them. So you know how many arguments there. But sometimes there are reasons to have variable arguments functions. So even if you have been programming in C, you probably never develop a function like this, but you have been using functions developed this way. For example, the printf function is an example of a function with variable arguments, and you have been using that since probably your first or second C programming class. You can call printf with one argument. You can call printf with 5 arguments or even 20 arguments. So printf is just a C library function. So it also has to follow C standard. So C library function can implement variable arguments. You can also do that. So to implement such a function, you need to take advantage of the C type VA underscore list. So which means variable arguments underscore list. This is a type defined in C library, and this type is defined in std_arg.h. And there are 3 associated functions as well. There are va/start, va not slash, va underscore arg, and va underscore underline end. So obviously, like I said, va stands for variable arguments here. So let's take a look at this concrete example. I downloaded this program from this URL. You can just you can click this link to find the source code. So in this simple example,
Hello.
yeah, question?
No, sorry.
Okay. So in this simple function, we want to compute the average of some doubles, right? And so in say there are integers, there are float numbers and double numbers, right? So here we want to compute the average of several double numbers. And this function is defined this way. The prototype of the function, the parameter side only define int, which is the number, which is a number of integers, number of input, number of argument you are going to use when you call this function. And everything else is not really defined. You didn't define this is a double, right? You only use 3 dots to tell the compiler this is going to be a function that can take variable arguments. Then at the beginning of the function, you define this var list. Then we have a double because our input is expected to be double. Then the integer I. Then we tell the C library that our variable argument list starts with that number variable, which means the number variable is the last one that we know the type. Everything after that will be we don't know how many are there, we don't know their type. Then we have a for loop. Then we first assign to 0, then I should be smaller than the number. Then the sum equals to just plus equal to, here we use the function variable argument underscore arg to retrieve the next argument on the stack, because we're supposed to put the argument on the stack, right? And to retrieve the next argument, we have to tell what is the type of the argument. So actually I made a mistake. So we are actually adding integers. We're not adding double numbers. So here we're telling the program that we're telling the C library, please retrieve the next argument on the stack. And that argument type is an integer, is an int. So if you call this the first time, it will work. Remember, in C, the arguments, they are pushed onto the stack from the rightmost to the leftmost. So for example, here we're calling the average. We're calling 4, 2, 3, 4, 5. We have 5 5 arguments here. But the first argument is the integer number. The other 4 arguments are the integers you want to compute their average. So, excuse me. So when they are pushed onto the stack, 5 is pushed onto the stack first, then 4, then 3, then 2, then 4, right? So that's how the compiler will order the arguments. And this va underscore arg will retrieve the next argument, which is 2. That's the first time you call that. The second time you call it, it will retrieve the argument 3. And the third time, 4, then 5. Then add them together, then we get the sum of them, right? Then after you are done with this, you need to tell the library, I'm done with the variable arguments with the va underscore under here. Then we just return sum divided by number, so we can get the average. So how to use this function? We can call this function. Here we are computing the average of 4 integers. The second time we call it, we are calling it with 4 arguments, and the first argument is the number of integers we want to compute the average, and the next 3 arguments will be the numbers we want to compute that up. So if we just run this program on our server, So if you go to average 32, so if you just run this program, it works as expected. Okay, so this is how you can develop a function with variable arguments. So this feature is actually different from the C++ feature of function overloading. I remember C doesn't really have the function overloading feature. So some of you probably program in C++. So in C++, you can define two functions with the same name, but they have different parameters. They may have the same or may not have the same return value, but they must have a different parameters. So even though at a C++ source code level, the functions have the same name, but after compile, they will be compared to totally different functions. For example, the first function takes the 3 arguments and you compute their average. The second one takes 4 arguments, you compute the average. So this is totally different from the function with variable arguments. This is one function, and this function overloading is many different functions. So if we compare this program, you can also say that they are much different. For example, the left-hand side, we have the 32-bit, the function with variable arguments. This is just one function. On the right-hand side, you can the C++ overloading version. First of all, you can see they will have different labels. In C++, the label is average III. There is a underscore Z7. The 7 here means the function names, function name length. In this case, the original function name is average, which is 7 bytes, 7 letters. That's why there is 7. The next function is also 7, right? Because it's average. However, one function takes 3 integer arguments. That's why it's III. Another one takes 4 integer arguments with III. So these are compiled into 2 different functions. Okay, so next we will talk about the format string functions, which obviously use a format string, and also format string functions. They are all functions with variable arguments. So the format string functions, they can convert C data types such as integer, double, float to string representations. And to do so, you will need the format string to specify the type of those data. So there are many different format string functions. Someone you are familiar with, like printf. There are also someone you are not familiar with. They do not necessarily output to the stdout, which in our case is a terminal. Some of them will directly output to a file like a system.log. That one also has a format string function for that. So like other functions we studied before, the arguments, including the format string and other arguments, they are all pushed onto the stack on a 32-bit machine. The 64-bit machine, the same thing. They will go for the register first, then the more than 6, they will go to the stack. So depending on the data type, the caller function will push the value of the address of that value onto the stack. Sometimes not necessary address, can be the value itself as well, depending on the type. The format string function, which is also called, in this case, it's called the QUI function, where use the format string to determine how many arguments are there and what is the type of the next argument on the stack. For example, this average example, we didn't have a format string. However, we do have this step to tell the C library what is the type of the next argument on the stack. With format string, we will need the same thing. So you are probably very familiar with some of the format string functions like printf, f printf, dprintf, s printf. S is a string here. F is file. I don't remember all of them. What are they? But all of them are format string functions, and there are more format string functions. The common thing about this function is they take an input, which is called a format string, right? Like the printf, the very first argument you gave is a format string. For f printf, the very first argument you gave is open the file pointer. Then the second argument is a format string. So after that could be many different arguments. The dprintf, you gave a file descriptor, then you give a format string. Sprintf, you give a string first, the address of the string, then you give a format string. Okay. Like I said, there are several other functions you are not familiar with, like syslog. They are also format string functions. Also, there are some arrow functions, warning functions in the Linux library, and also the C library. They are also format string functions. So after all, what is a format string? You have been using it many times, but you may not know how powerful and how complicated a format string is. So first of all, format string is still a string. In C programming language, a string is an ASCII string, and a string ends with 0, right? Like any other C strings. So a format string contains text to be written, and it also contains format specifiers that can be replaced by values specified in other arguments. So if you have a hard-coded string, then you only have the text to be written out. You don't have any format specifiers. What makes format string different is the format specifiers. And a format specifier follows this prototype here. It always starts with a percentage sign. And there could be an optional flag field, an optional weight field, an optional precision field. But if you want to use a precision field, you have to use dots there as well. Then it can have a length field. Then it must have a specifier. So the specifier is not optional. You must have this part. And the percentage sign itself is just ASCII value 25 in hex. So if you say someone use /x25 or 25 in hex, that is equivalent to a percentage sign. So the format string function will pass the format string. We'll try to understand the format string and try to say what are the other arguments I should look for. Then look for those arguments on the stack. So if it's not a format specifier, it's just a regular characters, a string we need to output, then you will just copy that to the output. So as you can see that the most important part here looks like the specifier, right? The specifier is something you have to use. And so this is a full list of the format string specifiers in the C programming language. or we can say the C standard library. Some of them you are very familiar with, like percentage %D, we'll be using them, or you can use percentage %U, which means unsigned, or you want to print a hex value, you can use X, either lowercase or uppercase. Float number, you use F, right? Those are something you are familiar with. What is interesting is N. So we have several people here. Did any one of you use percentage sign N in any format string before? Anyone? No? Okay. So that percentage N is something surprising. Most people have been using printf for years. If they never carefully read the document, they didn't know percentage N exists. Percentage N will not output anything. Instead, it will write a value to the memory. So when you hear about writing a value to memory, you feel, oh, this is scary. You're going to change your memory, right? You're going to, maybe you can override the return address, maybe you can override some global variables, right? So that's one of the scary thing about the format string vulnerability, because the format string functions, they're very powerful. Also, P is to print out the pointer address. So besides the specifiers, you can also control flags, weights, and precision. Those are actually also important in attacks, which we are going to do, because you can use them to carefully craft exploits. We will say it later today, why they will be useful. Let's go through some of the flags. Weights is one actually quite useful. You just put a number there. You put a number there to tell how many bytes, how many characters printf should print out for you. And later we'll say that's actually very useful. For length, you do not only need to specify, so let's say for length, there are, you can just give a number. You can also specify a char, integer. I'm not going to talk about the detail of this table. Later, when we say examples, it will be much more straightforward. Okay. Now next, let's say several format string examples and the output of it, so we can understand those popular specifiers, especially. Oh, so here I don't really have the percentage N specifier. We're going to look at that later. Okay. So let's say the first one is printf characters percentage %C white space percentage %C white space new line. So the first, you can see that the first one, the whole thing is a string, right? That string is a format string. And in this format string, we have two format specifiers. They are both percentage %C. And percentage %C, if we go back to oh, sorry guys, Jeremy, come on. Can you close the door, Jeremy? Thank you. So you can say that percentage %C here is to print out a character, okay? So here, the first character we want to print out is a lowercase a. So when we use a single quote and lowercase a here, what actually pushed onto the stack is obviously the ASCII value of that, right? So the second character we want to print, we just gave the ASCII value of that character. In this case, it's just a here, an uppercase a. So the second printf, we have decimals Then we print out two integers. For integers, we use D, which means decimal. You can also use I. And the second one, we use L here, right? Instead of just D, we have LD. So that L is the length. You see here, the length, L. It means that we want to implement a long integer, not just a regular integer. Then we print out 1977, then a large value here. The third one, we do precedings with blanks. Then we also print out an integer, the same integer, 1977. However, before that specifier D, we have a number 10. And that number is not a length, is not a precision, because a precision you have to use dot precision, and that number is width. And it's also not flag, because only those are valid flags. So that's actually width, which means I'm going to print out the number. However, I'm going to print out 10 bytes, 10 letters, or 10 characters for it. In this case, the number itself, decimal, is only 4 characters, but we're going to print out 10 of them. And we didn't specify what. So since this one is only 4 bytes, 4 letters, we need to print 6 more preceding letters. So here we didn't specify what preceding letters to print. That's why it will print 6 white spaces for us. Also note here before the column and the percentage sign, there is also another white space, right? That white space is also printed out here. So the column, between the column and one here, there are actually 7 white spaces here. Then the next example, we print out the same number with preceding zeros. In this case, this 0 is a flag. Okay, so at the beginning we have a flag. The flag can be a 0. Okay, then the width is still 10. Excuse me. That's why we will print it out. We will print 6 zeros, then 1977. Okay. Next example, some different red dices. The first one is we're printing out the same number, just 100 5 times. The first time we print as a integer, the second time as hex. Then what's this called? Octal. Then here we are still printing it with X. However, we are showing a sharp here, which means this one. It means it will print out X here. Okay. So that's how we print decimals, hex, and others. For float numbers, the same thing. So float number, you can say our format string has a dot. We're printing out this float number in 3 different formats. And the first 2 of them has a dot. When there is a dot, means that's for precision. Precision means how many letters you want after the dot. So the first one, we only want 2 after that. That's why we're only print, even though the number we give is 3.1416, we're only actually printing 3.14, right? Then the next one, we're actually using lowercase e. If you go here, we say it will print out somehow exponential or the natural logarithm number. I'm not sure. Okay, so that's for float numbers. Also, the ways you can play some tricks using the start. So here we're only using 1 specifier, which is D. However, we gave 2 different arguments. That's because the star, when the when the program says start, it will also look for argument. And it looks for a start, it say, oh, I'm going to print 5. In total, print out 5 letters, and the 10 itself is 2 letters, then we are going to print out 3 preceding zeros in this case. And also we have %s to print out a string, the string itself. Of course, when you write a program this way, what was pushed onto the stack is not the string, the content itself. The string will be stored in the not writable, but just the readable, read-only memory region. And the address of the string is pushed onto the stack, not the string itself. Okay, so next, we are going to take a look at the %n example. This is a very interesting example because, like I said, most of you probably never used the %n before. In this function, we have 2 local variables, a and b, and they're local variables, so they are on stack, and they are initialized. Both of them are initialized in 0. So the first printf does a is %d semicolon, white space, b is %d, then new line, then a and b. So we'll just print out the value of a and b here, right? So this line will just be 0 and 0. That's very easy to understand. The second line is what is interesting. So we have a bracket here, changing a and b dot bracket %n 1 2 3 4 5 %n /n. I said before, %n means %n will not print out anything, even though this is a printf function. %n will not print out anything. However, the corresponding argument must be a pointer to assign the int. So we have 2 %n there. Then there must be 2 corresponding arguments, and both of them must be a pointer, which means it's an address. And that address, at that address, it should be assigned integer. And the number of characters written so far is stored in the printed location, pointed location. What does that mean? Let's say this printf. Okay, so this, first of all, this only applies to one function. It doesn't apply to the previous printf functions. In this printf function, we print out how many characters before the %n, let's say. So before %n, we just have a regular string, regular string. So when the printf say it, it's just sending to output. So how many bytes will be output? The double quote is not a letter we're going to print, right? It's just the beginning of the string in C language. The bracket, that's 1 character. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The white space is 10, 11, 12, a lot of white space, 13, 14, 15, 16, 17, 18, 19, 20. Okay, so before the %n, there are 20 characters, which means before %n, 20 characters has been written so far. So the number 20 will be stored at the address the %n points to, which is the address of A. So this one, the first the first percentage n is actually going to change the value of a from 0 to 20. So after that, printf keeps printing 1, 2, 3, 4, 5. So far, before that, it has been printing out 25 letters. The percentage n doesn't print out anything, but everything else together will be 25, right? So the next percentage n corresponds to the address of b. So the value b will be changed to the value of 25. So most of people do not know this feature exists. Okay. Now after that, we print out the a's value and b's value again. So obviously, a should be 20 and b should be 25. Does that make sense? Okay, let's keep going. The next example, let's say we have a percentage d here and 2% n. So let's count how many bytes printf has been printed out and what value should be a and b here. Okay, so you can see here, this part we already count. That's 20 bytes, right? From this bracket to this bracket, that's 20 bytes in total. How about this one? How many we're going to print? Percentage 0, 20d. Do you still remember what that is? That is print out an integer. However, we're going to use 0 as preceding fittings, and the length we'll print out will be 20 characters in total, which means this whole thing will print out 20 bytes, right? Plus the previous 20 bytes, that's 40 bytes. And there is another white space, which we're going to print. So then we're going to change. So to the first percentage n, we already print out 41 bytes. So a's value will be changed to 41. The second percentage n, between them, we didn't change anything. We didn't print out anything. So b will also be changed to 41, right? So both a and b after this should be 41 if my calculation is correct. So let's run the program, then we will know. So if we go to our server, go to our server, go to let's say format string n. Oh, oops. Save. It is the same as what we expected. It's the same as what we expected, right? So a and b originally has a value 0. So the first time we print them out, they have 0, 0. The second time, it will print out this string percentage n will not print anything. That's why after this bracket, we will have that 1, 2, 3, 4, 5. However, the value of a and b has been changed after this. So you can say a is 20, b is 25, same as what we calculated. Then the next one will be, however, they will be 41. Okay. The flow number, everything else, you can use the same approach to compute. So that is basically how percentage n works in the C standard library. Actually, some other extensions, like the proxy extension, they introduced some other tricks, like the n dollar sign, where n is the number of the parameter to display using the format specifier. So allowing the parameters provided to be output multiple times. Okay. For example, the proxy extension, you can do %2 $D, which means you should look for the second argument after the format string. Instead of the first argument, $2 means that. The second argument here is 17. That's why we print out 17. Then we can also do %2, which means the second argument. Then sharp X. So we are going to print out the hex value of that. That's why we get 0x11. Okay. There is a semicolon. That's why there is a semicolon. Then we have $1, which means look for the first argument, 16. Yeah, the same thing. In this class, we are not going to use this. We don't have to use this, but use this trick can make your exploits simpler later. So now you understand how format string works. You understand what are format strings, and there are some weird format strings you probably don't know before. You all know how to use them. So it's time to discuss the vulnerability. So how could this go wrong anyway? We've been using printf for many years. Why this could go wrong? Why this could be any vulnerability? The vulnerability exists when the user can specify what is a format string. Most cases, like the previous examples, those ones, the format string itself, this string itself is hard-coded. It's hard-coded in the program, it's hard-coded in the read-only area of the program. It's a string itself. However, because it's a string, right? So the implementation of this is actually, this is an address. When printf look for the first argument, the format string, you look for an address. And that address can be a hard-coded string, and it can also be a user-specified string, right? So it's possible to directly use user-specified string. For example, we have a function. The function takes a user input string, then directly feed that user input string to printf. This is totally legal in C. However, this string user-specified can have percentage sign, can have format string specifiers, because it's supposed to be a format string. And because of that, there may be many problems. We're going to say that in a minute. So the correct usage of this is you should always hard code your format string. In this case, the user input can be printed out, but should not be directly fed in the format string. So in this case, even user's string has a percentage sign, it will not be escaped. It will not be considered as a format character. So let's look at our first format string vulnerable function. We have a main function here. Main function simply returns the vol_foo function. Vol_foo has a local variable, which is an array of characters, 20 bytes in this case. Then we have two printf functions. The first printf function, there is no vulnerability. This one, no vulnerability. It just print out what is your input and the new line. That's it, no vulnerability. Then there is gets. Gets is to get from stde. So of course, first of all, the vulnerability here is you can say there is a buffer overflow, right? The gets may output, may return more than 20 bytes to this local buffer. and that's buffer overflow. But that can be divided by a stack clearing. We already studied that before. Then the second vulnerability is here. The user input is in X, and the user input is directly used as a format string in the second printf. And that's where the vulnerability is. Okay, so let's run this program and see what we can do with this. Format string what? So for this challenge, I do not really require you to get the flag for this one, but this one actually you can get the flag. Anyway, we run the program. The program asks for my input. Let's say my input is just a hello. The PN is quite slow. Whatever. Then it print out hello. That's it, right? What if instead of giving it a regular ASCII string, I give it a format string? Let's say I give a %X. What will happen? So if I give it %X, it is like I directly put the %X here. So the printf function will look for the argument correspond to %X, which I didn't really give. I only give one argument, right? But printf will consider there is an argument after the string %X, and that argument should be an integer, and we are going to print the hex of that, all right? Since we didn't give anything, the function will just look for the parameter on the stack for that. So when we print this out, for example, oh, sorry, that's my own terminal. So then when we do this, what do we get? We get a value on stack. That's a value, right? We can actually print many of those. Let's say to separate things a little bit, I use a dot between them to make it, oops. So let's print out 3 values or 4 values. Now we're going to print out 4 values. Each of them is 32 bits, 4 bytes on the stack. And we see the value. 7F something. What does this look like? 7F looks like an address on the stack. After that, there is a 0. After that is 5655. That actually looks like a code address, right? That probably is the return address. That is the return address of the function calling printf. After that, there is another pointer, right? So we can actually do a quick check to say if that is let's go back. Oh, I didn't say, oh, so this is not a. So I think that address is the main function's address. Let's debug this program to figure. We debug this. We just run it without. Oh, I should print out the address first. I should let's do this symbol for the main function. So the main function is at 56, 55, 62, 99. The address we have there is 623D. Okay, 623D. 623D. 3D. The 3D is actually before that. Let's say which function. What's the source code there? Oh, should be the Volfu's function address. Sorry, should be somewhere in Volfu. Let's say, let's see. Okay, that's actually this address, 623D, and that is right. That's the address right after we make the function call to this function. Then after that, this function calls puts, right? So that is an address on the function on the stack. So we can also. So how do we crash the program, for example? Now we say that we can read whatever on the stack as long as the address is higher than our format string address, right? We can actually also crash the program by just using %s. Do you remember what is %s? %s will use whatever on stack as the address and treat that address as the address of a string, which means there is a level of dereference here. So some of the addresses are not dereferenceable, like the percentage, I'm sorry, not percentage, like the if we output two things, you can say the first one is a value, looks like maybe dereferenceable, maybe not a string, but dereferenceable. However, the second one is 0. So in C language, 0 is not a valid address. So if we dereference 0, where the program is going to crash. So if we only have one %s, probably it will not crash. Yeah, it doesn't crash. It just print out something random on the stack. However, if we have two %s, the second %s, we are going to dereference that 0. That's not allowed. So it will crash. Oh, actually, this one number crash. So the new program that crash is just the printout. So the newer version of print, you will say that's a law byte. You should not dereference that, but it will not crash. Okay. So maybe some others addresses where it will crash. Let's just have several %s here. As you can see, some of the addresses, some of the values, they are not 0. Okay, so say cannot do a special treatment, say that's law byte. Instead, it tries to dereference that because it looks like an address. However, nothing is there. Then the program crashes. We get a second point. So going back to the slides. So I'm going to show you some animation here. So hopefully you can understand what happened for we just demoed it. Okay. So left-hand side, this is the program we have. This is a disassembly of that Volfu. So right-hand side, we have the stack. So Volfu has its own return address and saved EBP. And this return address should point to somewhere in the middle of the main function, right? Because Volfu was called by main function. Then after that, there is a query. Then after that, there is the local variable s, this s, local variable. After that, it will make several function calls. For printf, gets, another print. So in the second printf, imagine that we're already done with the first printf and get. In the second printf, it's also a function. So its own stack string is also on stack. And it looks like this. It has return address, and this return address should point to the middle of Volfu. right? Then it has saved EBP, right? Then after that, go higher, we should have its argument. And the first argument is just S, the format string, which means the first argument here is the address of that, where the address of where S is. That's it. Then when we do a percentage X there, when we do a regular string, that string will be copied here. Then for the printf will not look for more arguments, right? It only believes it has only one argument. It will not look for other arguments. So it will not read this part. However, if you have a percentage X here, a question?
అంటే లైక్ నేను అక్కడ బిర్యానీ తిన్నాను సాయంత్రం
You have a question?
ఇందాక సాయంత్రం మళ్ళీ
Okay, I think that's a mistake. Okay, anyway. So if we have percentage X here, then the printf function will think that besides the format string, there should be two arguments on the stack. So the second argument will be the first argument address plus 4, right? The third one will be plus 4 again. However, at those addresses, we didn't put anything. We didn't input anything. We only input to the S. So whatever is left there will actually be printed out. And you see that what left there was some return address. That's actually the previous printf and the gets used those address. And also other functions use the address. However, this is a stack. No one cleaned that up. The value was there. So if we have multiple, even more, which means if we have even more percentage X, we will eventually be able to read the calorie. We will also be able to read the saved EBP and return address. Everything, right? So let's try that. We put a lot of percentage X here. Let's do 4 first, and then let me copy this. Let's print out that's for each percentage X has 4 bytes on stack. That is, we're printing out 48 bytes on the stack. And to say, what do we have? Oh, stack smashing detected. So we already touched the, that's too many. Let's go one. Oh, even that will detect that. Even 8 will be too much. 6 should be okay, right? Yeah, let's say then we do 6. We could get more values on the stack. So here is actually another protection is when we read the calorie value, it also detects that. Okay, I hope this here makes sense. Okay, so we already say how we can view the stack. We also say how we can crash the program. Then let's move to the second example here. In the second example, we are going to use this format vulnerability to read something. We're trying to read something in the memory. So in the source code here, I'm not showing you what are the secrets, but I'm telling you that there are 2 secrets. They are strings, and they are at 2 locations. We call it P1 and P2. There is a vulnerable function. The vulnerable function has a buffer, which is 120 bytes big. Then there is a gets. But this program is protected by standard canary, so it's not easy to bypass that. To just inject your share code or arbitrary code. However, there is a printf vulnerability, and we want to use printf vulnerability to steal this information. Of course, you can steal this using buffer overflow, but that's not what we're going to do today. We're using a different approach. So you can see that our input, user input, will be directly used as a format string here. Then the function will return. The main function will print secret are at this address and this address. Can you read them? This printf doesn't have vulnerability. Okay. So any idea how we can do this? Let's first look at what the stack looks like. This is a Wolfu. The stack has return address, saved EBP, there's a canary, and there is a temp buff. And temp buff is at this address. EBP minus 4084 here, as you can see here. But for this one, this address doesn't really matter that much. We're not going to use that address. So let's run a program. Format string 2. Format string 2. So in format string 2, we run this program. It tells us secret are at this address and this address. Then give us chance to input the format string. So how can we read them? So to read it, what do we need? How do we print out a string? Any idea? How do we print out a string? We print out a string, use what? %s, right? Which means we have to use %s here, right? However, %s will look for something on the stack. We'll look for something on the stack. And what it looks for should be the address of that string. So we can put the address of those two things onto the stack. Then eventually make this %s, the first one correspond to the second one, to the first one, and make the second %s corresponds to this value on the stack. Then the printf function will automatically print the secret for us, right? Then let's try this. To make things a little bit easier, I'm going to write things in a file, and so we can keep the record, try multiple times instead of just every time I need to retype everything. So let's say our exploit may look at this at the very beginning. We put those two addresses onto the stack. Those are 08, 70, 55, 56. Another one is, of course, you can also put this in environment variable, right? Don't have to put this on stack. But one way to do this is on stack. Okay. So next class, I will show you guys how to do this in environment variable. 55, 56. All right. So after this is something we want to use as the format string, right? So to make this easier for us to understand where we're at, I put two underscore here. Then let's put a %s. So we put this one in our No. Put. That's EXP. That'll be good. Then we just run this program. Then all the input will be from the exploit. Okay, so what do we get? We get a segment port, right? So which means the percentage S doesn't really map to this address. It didn't map to this, correspond to this address. So how can we make it correspond to this address? How do we do that? So we can actually, because this thing is on stack, but we don't know where it is. Because this will be a local variable of the function value. However, we don't know where is printf's first argument and the second argument, right? That's why we can try by having a lot of percentage X here. If we have a lot of percentage X, eventually it should print out the things on the stack and it should print out those values for us, right? Let's try again. So now we have 7% X. Then what do we print out? The whole thing, first of all, the whole thing is treated as a format string, right? The first part, this part, doesn't have a percentage sign. So it's not a format specified. So printf will just output whatever we have here. Some of them are not printable, but some of them are printable. For example, P, let's go to ASCII table. As you can see here, 70 is F. Oh no, sorry, 70 in hex. 70 is P, right? So the first 8 in hex is backspace. It's not printable. However, the second 70 is P. That's why we have a P here. Then after that, we have a 55, 55. 55 is uppercase U. That's why we have uppercase U here, right? Then here we give 8 bytes, but only 6 of them are printable. Then after that, we print out the 2 underscores. Then we are going to print out the values on stack. Then let's say if there is a value we want. Let's say, oh, what's this? 56557008. That's exactly what we put on stack, right? So those 2 are actually, which one is this? This is the first percentage X, second, third, fourth, fifth. So the 5th percentage X maps to or corresponds to the address we put on stack. So if we do not use those, sorry. Yeah, so if we do not use those 2 underscores, the output value will actually be different. You can say it doesn't. Let me see. Oh, they do not really change. They do not really change the pointer, so the value doesn't matter there, right? So we still get this, right? Okay. So then I think maybe it's clear here, which means we're going to replace the 1, 2, 3, 4, 5, the 5th percentage X to what? Here is 1, 2, 3, 4, 5, right? Percentage X to percentage S. Okay. So what will this format string do? It will also just print out this part. Let's print out the 2 underscore here, or anything else. Let's to equal signs to separate them. Then after that, we're printing some value on stack. Print some value on stack. Then we will print out a string whose address is on stack, right? This one should work. Okay, see, it works. It first print out the format string as the ASCII string part as we expected, then print out whatever is on stack, right? Those values. Then after that, print out this is a secret. This is a secret 1. This is a secret 2. Okay, you see, this is how you get the 2 secret from this. So let's say maybe there is an easier way to do this. Instead of putting this address on stack, we put the address in the environment variable, right? That's another way to do this. Let's just get a 1. I may change this a little bit to later to just use just a 1. To use just 1 string, because 2 and 1 are the same thing anyway. Okay, let's say that we do a environment variable to do this. We export. Let's just use the address format. Actually, it's not really the format address, but whatever. We'll do Python 2. So we just needed this address, but we have the same issue as before. If we only have 1 copy of this address, then the chance for us to hit it very low, right? So let's just make 1,000 copy of it. Now we have this environment variable. We print out, it should give us a lot of POV there, right? If it's set up correctly. What's going on? Why it's not?
You have address F and address R.
Yeah, the typo. Yeah. See? Okay, we successfully set up the environment variable. We try to get its address. Okay, that's our address. So then go back to this. Next here. So the exploit now will look different. The exploit. Okay, what I'm thinking here. The string is already there. Oh, actually, we still need to do that. Because we cannot put this address. We cannot make this address corresponds, or the address higher than this corresponds to %s there. Yeah. I didn't think it through this one. So we have the address. We have the address of the address. %s there. Oh, okay. This would still, because there is another protection here, so it doesn't work. Because we're going to read the query, so it doesn't work. Okay, sorry about that. I need to think more to make this approach work. I forgot about that 2 levels of address instead of 1 level of the address. Okay, so let's move forward. So I give you one approach. The format string, the environment variable approach actually is not that straightforward. I need to think a little bit, make it work. Okay, the third example, this one, I'm trying to get the flag. This one, there's a vol foo has two buffers. Each of them is 100 bytes. So we'll have f get our input to buffer 2. However, we're only getting 99 bytes and the new line, which means there is no way to overflow to buffer overflow 1 or even higher, right? There's no way to overflow that. However, there's another vulnerability is sprintf, which has buffer 1 and buffer 2. Buffer 1 is the target. Sprintf, the first argument is not the format string, but the target. F2, buffer 2 is the format string. So still, whatever our input is, it can only be 99 bytes. But whatever our input is will be used as a format string. And we already know that for a format string, you can generate many more bytes, right? For example, you do a percentage 20D. Even the integer you gave is 4 bytes. You can actually generate 20 bytes, right? So that will help us to overflow the buffer and also overflow whatever is higher than that, which means we will be able to overflow the save the EVP and return address in this case. Okay, so let's take a look. This is a disassembly of the format string. After analyzing the disassembly, we can say buffer 1 is actually at EVP minus 108 in decimal. Buffer 2 is actually at EVP minus 208 decimal. But this here is not what we're going to overflow. Buffer 2 is where we are going to put our format string. And buffer 1, the format string is whatever generated from our format string will not be output to our terminal since we are not using printf. Instead, it will go to the buffer because it's sprintf. And because of that, we will be overriding the whole thing, right? So this one, there is no canary there. So how do we do this? We just put share code on, we put share code on stack, then we just overwrite the return address. That's it. Huh? Let's try that. Question? This is Walmart. 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 Okay, so let's first put our share code on stack. So this is our share code. Let's do 1,000 bytes of knobsnet. Everything looks good, I guess. Okay. So now we have our share code. Then we are going to have our export. So first of all, what should we put at buffer? We should put, because this place is 108, right? We don't really care about what the value is. So just 108 bytes of garbage, right? Then another 4 bytes of garbage, which the value we don't care. Then just a return address. right? Looks easy. So it's just 112 bytes of garbage to cover this part, then 4 bytes of return. So to do that, our what I'm trying to do. I'm trying to write the I'm trying to write the format string. Okay. So our format string should be then like that 112D, right? We know that percentage 112D will give us, will write 112 bytes at buffer 1, right? That's it. Then after that, we will need the address of our shellcode. And we just use here we have DAAD, then we just use DB FF, right? That's our shellcode. That's our exploit. So this one we just need to do directly go there. Okay, it works. So if we do not have 112 bytes instead of 101 bytes, then only the first three, only the higher 4 bytes, the 3 bytes, are put into the lower 3 bytes of the return address. So we're going to return to someplace. Oh, actually that works. Because most of oh no, that work. Yeah, it will return to FFFFFBB, right? So that will trigger a segment fault. It doesn't work. Sorry. Yeah. If you do 113 bytes, obviously it won't work either, because that will return to FFBB11, then would be some random value, because we didn't specify which integer corresponds to this. So it will some random integer corresponds to that, and that will fill a bytes there, right? So that will also be a segment fault. Okay, so that's an easy one. Okay, I guess that's what I want to discuss today. I'm going to change format string 2 a little bit, maybe tomorrow. The homework will due on Tuesday, a week from now. So this Tuesday, the coming Tuesday, you will have the homework due for last week's homework. After that, we will I will give you guys another week to do the homework of this one. Okay, so that's the first part of our format string, and next week we will talk about several more examples of format string. Especially, we will go for the percentage n and how we can use percentage n to override things on the in the memory in memory. Okay, any questions? Okay, thank you guys for showing up. See you guys next week. Have a good night.
Thank you. Have a nice one.